All right, Mr. Sams, we've been learning about.
Yeah, you've got to figure out what a tope is.
Yeah, what the heck is a tope?
I don't know, but you said it has something to do with atoms.
So yeah, we're gonna learn about something called an isotope today.
Okay.
Okay, so let's do just that. Okay. Well, here's what an isotope
Oh,
is.
wait, same.
Yes, there's that word, same.
Okay, so that's the iso part.
Uh-huh.
So we have the same atom.
With a different mass number.
Okay, so same atom means it has the same number of protons, because different number of protons make it a different atom.
That is correct.
Okay, now
so
we're getting
tope
somewhere.
must mean, I don't know for sure if this is true, but I'm going to call tope equal to protons.
Protons or the atom.
Yeah, maybe
Good.
something like that. So we're going to learn about isotopes today. So it's the same atom with a different mass number?
Mass number, that's a new one.
Well, mass number makes sense. Mass is what?
How much stuff there is.
Yeah, so if you get so much
matter.
stuff, so the mass number, that number is like a number, so it should be like, it's how much it weighs, sort of. It's not weight, it's mass, I know.
All right.
Yeah. Now, why don't we take a trip to the grocery store?
Okay, well, we're making this in Sioux Falls, so let's go down to the local grocery store that's close to our hotel.
What's the name of that place?
I don't know, Sunshine
Market or something.
like that?
Okay,
Yeah.
cool. Well, here I am in Sioux Falls, South Dakota, at the grocery store. What's it called, Mr. Sam?
Sunshine something or other. Sunshine Foods,
or something
yeah.
like that. And we want to talk about isotopes. I know it's a very weird place to talk about isotopes, but we've got some stuff. I mean, what's the best place to shop for science supplies?
The grocery store.
Hey, so let's look down here. What I have is I have 3 cans of Hunt's tomato sauce. Hip. They are 15 ounces each, and I have 4 cans of 8-ounce tomato sauce, Hunt's, of course. So the question is, what is the average atomic weight? So if we were to consider each of these an isotope, this isotope with a mass number of 15, this isotope with a mass number of 8, what's the average? Well, if you take 8 and you take 15 and you average them, well, that'd be 23, like 12 and a half. But the problem is, I have more of the big one, more of the small ones than the big ones. So what is the average atomic mass of a Hunt's tomato sauce?
Let's do the math.
I think we should do that. Well, Mr. Sams, that was interesting.
It was.
So what do we have again?
Well, we had the cans of tomato sauce.
So how
we
many
had
of each?
3 15-ounce cans.
3 15-ounce cans.
Uh-huh.
Okay.
And then we had 4 8-ounce cans. So we wanted to determine the average mass.
So what is
or
the average?
Yeah, number of ounces of those things. Now,
shouldn't I just take 15 plus 8 divided by 2,
well,
right?
if you can, if you have equal numbers of things, but we don't have the equal numbers. We have 3 of one, and we have 4 of another. So we're gonna have to do a weighted average.
So how do we do a weighted average?
Well, you're gonna have to take the mass times the
percentage.
percent. Yeah.
Okay, so we're going to probably figure out that percentage. So if we have 7 total isotopes, then we would have the 15-ounce size. That would be 3 over 7, right?
Yep. And so that's 42 point. We'll call it 9%.
And of course, then we do 4 over 7.
Yep. So that
the other one, and that would
syntax
be-
error. Well, it's 100 minus that. Sorry, I can't
That'd
use
be
the calculator today.
57.1.
57.1. Yeah, I guess we could have just subtracted that from 100, huh? I'm too lazy. I like to use the calculator.
You are like my students too much. You must not always use calculator, Mr. Sands.
I know.
You must learn how to do this.
That's what the kids would be doing right now, so I was just trying to do what they were
imitate the
doing.
students.
Exactly,
I see. Okay,
yeah.
very good. All right. So let's do this math here. Okay?
What kind of accent is that?
I don't know. I figured it out each time.
Okay.
All right, so 15 times what?
15 times the percentage as a decimal.
So how would I write that?
That's going to be 0.429.
And you got a calculator.
I do.
You
So
can
15
just
times
those numbers.
0.429. I'm kind of lying down the job here. 6.44.
6.44. Okay, and then you'll do 8 ounces, and you'll times that by a decimal 0.571.
So we don't use the actual percentage. We use it as a decimal, and we get 4.57.
Okay, and now what we do?
Now you just got to add those two numbers together.
Yeah, you simply add these guys. It's how we do weighted averages. This is how you calculate your grades, by the way.
Yeah, so yeah, if your teacher has 80% for tests and 20% for worksheets, you can't just add them up and divide by 2. You actually have to multiply by the decimals.
Okay.
All right, so this is when we add them together. When we add them together, we get 11.01. So the average mass of the cans of tomato sauce that we have would be 11.01 ounces, and that's a weighted average.
But that seems kind of weird, Mr. Sams. None of them weigh 11 ounces.
No,
Either
they
weigh
don't.
8 or 15.
Yes, they do.
But they weigh 11.01?
Yeah, on average they do, based on the distribution that we had between the 15 and the 8-ounce cans.
But the weird thing about that is that nobody weighs 11.01.
That's true,
It's either
but that-
15 or 8.
Right, but if we have that distribution, then that's our average.
Okay, all right, that's cool.
All right.
All right, so now let's go back to this concept. What makes an isotope have a different mass? What is the key thing that makes the difference?
Well, the protons are the same.
All right,
Because it's the same element.
So protons
So it's
are
not-
same, then if their mass is different,
Then it has to be based on the different number of neutrons.
yeah, that's it. So it's the neutrons that make the difference, folks.
Mm-hmm.
If you have a different number of neutrons, then you have a different mass number.
Yes.
Okay.
All right.
And so if you look at this cool picture, the blue represent the protons with a positive charge, and the red are the neutrons with no charge.
Right.
And if you get more red things, then you change your mass, or less red things for that matter. Yeah. Okay. Okay. Now let's take an example from a real chemical, and that would be
Okay.
hydrogen. So if we look at hydrogen, what do you notice about hydrogen?
It's got one proton and one electron.
So this is hydrogen that weighs 1. The mass number is always written on top here.
Uh-huh.
So the mass number of this isotope of hydrogen is 1.
And what's that number on the bottom there? The mass number's on the top. That
This
one
is
is
the atomic number.
Okay, and that's the number of protons.
So this is the mass number, and this is the atomic number. The atomic number is the number of protons. And so there is just one proton and then one electron in this atom of hydrogen. Now this atom of hydrogen is different. Notice it has an additional
A proton and a neutron.
neutron.
So the atomic number is still the same, 1, but the mass number is 2 because I have one proton, one
And we
neutron.
learned this last time in the last podcast about how you can just subtract the mass number minus the atomic number to get the number of neutrons. Which
Okay,
are just the
so
2
it's
minus
still
1.
hydrogen, it just has a different mass.
That's correct.
Okay.
And then the third kind of hydrogen has 2 neutrons and a proton, and his weight is 3.
So it's still hydrogen because it has one proton, but it has a mass number of 3.
Correct.
Okay,
So the
those
difference
are the
is the
different
neutrons, and also the other fact is, of course, their
mass as a
is
result.
different.
All right, so those are the isotopes of hydrogen.
Okay.
Cool.
So let's make sure we understand this piece: the difference between atomic mass and atomic weight. Okay. Atomic mass is the mass of one single isotope. So if we go back to our analogy, it weighs 15 ounces. That one, the larger can of tomato sauce.
Okay.
Or it could weigh 8, right?
Okay.
But the average, or the atomic weight, is the weighted average. That was the 11 point.
And that's the one that shows up on the periodic table.
Yeah,
So when
this
I
is
look
what-
this up on the periodic table, that's the number that I see. It's the average of all the isotopes.
That is correct.
Right.
Okay, good. Okay, so if you actually, here is the periodic table, and so if you look at like iron right here, hard to see that, but his weight is 55.845. Now, the thing that's funny about that number is that there are no iron atoms that weigh 55.845.
Right, because those are all, yeah.
Because this is
it's
the
either going to be a
weighted
little more or a little
average
less. Right.
of the different isotopes. One might weigh 55, one might weigh 56, or something like that. Okay. Now, let's do an example with some math. All right, Mr. Sams, what we want to now talk about, of course, is the example here. We got rubidium with atomic weight or mass number of 85, and also another one that weighs 87. We know their percentages. What is the average atomic mass of rubidium?
All right.
So we're going to do the same thing that we did earlier. And so rubidium 85, 85? Yeah. 85. That's his atomic mass.
Okay.
We would then times that by the percentage, which is 0.722, and that comes out to,
61.37.
okay, and then rubidium 87 has a mass, or a percentage of 0.278, or 27.8%, and you get,
24.19.
okay, and then of course you'd add them up. Watch, folks, as Mr. Sams adds these two
All right,
numbers up on his calculator.
24.19. It's amazing, isn't it? Plus 61.37. I bet you could have done this in your head faster than I did on the calculator.
I could, actually. Yeah.
85.56.
Okay.
Now, does that make sense? Let's look at the masses. The masses are 85 and 87, and we have more of the 85 one.
So it should be closer,
So it should
to,
be
the
closer to
85
85.
sign, and it is. It's,
And
got,
it is.
it's higher, yeah.
So that makes logical sense.
Okay. Now
Okay.
let's do one kind of in reverse. This is
Okay.
the one that everyone struggles with. So the percentage abundance of chlorine 37, what is it? Given the fact that we have chlorine has an atomic mass of 35.45. And we're given the actual values for chlorine 35 and chlorine 37. So this is actually kind of doing that problem we just did a little bit backwards. So to do that, actually, let's get a bigger screen because we're going to need some more space, I think, on this, Mr. Sams.
Okay.
So you got the numbers memorized in your head?
No.
Okay, let's get a blank screen to do this, okay?
Okay.
All right. Very good. Okay, so what you're going to do is take the, what's the weight of the first one, Mr. Sam?
34.969.
And that's going to be times by the percentage, right?
Right, which we don't know. Can we call it X?
How about we call it X?
All right.
So if we multiply those together, that would be what?
34.969 times X, or X.
Yeah, that's pretty easy, isn't it?
Okay.
And then the other one weighs what?
36.966.
And we'll times that
Call it
by
Y.
Y. Okay. So then that will be equal to 36.966Y. Now we
Yep.
add these up. What do they add up to?
35.45.
Okay. So, wait a second, Mr. Sams. I have a problem.
Yes.
X and Y, and I only got like one equation.
Yeah, you need another equation.
I can't do it!
Yes, you can!
No, you can't with one
Yeah,
equation. My math teacher taught me.
Well, let's get another equation.
Oh.
X and Y.
Oh, X and
the
Y.
percentages have to add up to 100.
So X plus Y.
It has to be 100. Well,
Sort
except
of.
we don't write them as percentages, we write them as decimals, so the decimals will always add up to 1.
Ah, we have two equations and two unknowns. This is easy. man.
Yeah, exactly. Now we just, instead of having Y,
Yes.
Y is equivalent to 1
Y
minus X.
equals 1 minus X.
There we go. So let's plug that guy into Y.
So this is, guys, how we're going to do this. So it's like 34.969X plus 36.966 times the quantity 1 minus X.
Huh?
Now, because this, I need to distribute the 36.96 to both of these. This is an algebra thing. You guys have seen this before in your algebra class, so this should not be terribly hard. All right. Actually, I should say
Equals 35.45, because they all have to add up to the average.
And then I'll say plus 36.966 minus 36.966x equals 35.45. Now, my math mind is going, I've got x here and I've got x here.
So they need to go together.
Yeah, and this is a negative, so we're going to get, if you to subtract these two numbers, that'll give me my x term. What do you think?
34.969 minus 36.966.
966.
That gives us negative 1.997. X.
X. Now, if I subtract 36.966 from both sides, what do you get? This, of course, adds up to 0. This adds up to another negative number, negative 1 maybe, or something like that.
We get negative 1.516.
So that would be equal to negative 1 point, what's that again?
1.516.
Now, how do we solve for x?
Divide both sides.
By negative 1.997. These cancel. X equals what?
0.7591.
So that'd be in percentage land. Let's put that up here.
75 point.
75.9%.
Yeah. Now they always have to add up to 100, so 100 minus that. Whoops.
And so actually y is equal to what? 24.1%.
Right.
You're doing that on your calculator.
I'm just showing them what they would be doing, because they're going to do it in their calculator.
Because I think the question was, if we go back a screen, what was the percentage of the chlorine 37? The 37 is the one that weighted 36.96. And if we go back, that was the Y.
24.1.
So the big answer is 24.1%.
Yep. And you'll get some practice on that in class.
Yep. All right. I think they're done with the isotope.
Yes. I still want to figure out what tope
I think
means.
tope must mean protons.
We'll have to look it up.
What does tope mean? All right, we're doing this in a live audience. Does anybody know what tope means, you chemistry people? Nobody know what tope means. Okay, that's fine. And the cell phone rings in the background. Very cool. Have a good day. We'll see you in Internet land. Bye.